Okay, so there was one question that I want to reiterate. What is our purpose of turning everything into this canonical view volume? So why do we do this? It's already in a rectangle, it's easy to project. So why do we use this canonical viewing volume? There may be many reasons behind this choice, but one of the thing is it's after certain points in forward rendering pipeline, there's a step that is called clipping and culling. Clipping is partially cutting objects parts that are so that only parts that are inside the viewing volume are processed during rasterization, because all these things, the interpolation step, we don't want to do any interpolation for objects that we're not going to see anyway. Culling, which is written as which means removal, complete removal of objects, means that again we completely remove them so that they are not propagated into the subsequent steps of the forward rendering pipeline for efficiency. So clipping and culling in this standardized volume, the canonical view volume, may be easier. And imagine you have some hardware implementation in your hardware that just treats all the units between -1 and 1. Because if the hardware may not be configurable so that you have these LB minus n arbitrary units, arbitrary boundaries. If you want to implement this in hardware in a non-reconfigurable way, you need something standardized, a standardized coordinate system. I think that's also one of the main reasons that we have everything between -1, 1, and 1. So the units are now standardized. Everything we are going to be seeing will be inside this regular cube. It becomes a standardized coordinate system, basically. Now let's continue with perspective projection. So this figure is really nice. That shows the difference between orthographic projection and perspective projection, and it also shows one of the objects that are outside here. It's never visualized in our image, as you can see. And this is a virtual world which contains 3 spheres, but the green sphere is always outside the viewing volume. So when you look at through your image window, by the way, this near clip plane seems like a small image plane, but it doesn't mean the resolution of this image is small. It may be a smaller area in this real world, but when we see them on our screen, depending on the resolution of the image, we are going to see both the image here in this near clip plane and in this near clip plane of same size. We are going to see both of them, for example, as 2 megapixel images. Okay, this being small doesn't mean that its resolution is small. Because we have infinite resolution here in continuous floating point division, but also, I mean, since our precision is not infinite, we may not, we'll have some discretization errors, of course, since we don't in practice have infinite precision, but the difference most of the time of these resolution differences is negligible in most of the cases. I just wanted to remind you that this image that you see here on the left, although the near clip plane, although it's small here, the image sizes, they will be the same if the resolutions of these two cameras are same. Now, and as I said, this figure shows a really nice comparison between how orthographic projection is going to look like. We have all the spheres are the same size. When they're projected in orthographic projection, they're going to appear exactly the same size spheres on the image plane. But since this red sphere is a little bit farther away, when we use perspective projection, this farness is going to, far away objects are going to appear smaller on the image plane, as emphasized here on this figure, where we have the red sphere, although it's same size as the yellow one, it appears smaller on our image plane. So this is how we naturally see, and this is how we did in ray tracing. Now, how can we establish perspective projection with matrix multiplication, just like we did for orthographic projection. Okay, so this is, as you can see, this is another 4x4 matrix, which means that you can multiply it with your modeling transformation, camera transformation, and this one. Do everything in one step, because we can compose those 4x4 matrices into a single 4x4 matrix. Now, here's we have just like orthographic projection, in perspective projection, we again have six parameters. This near plane, this LRBT, is actually the same size as the orthographic projection. Therefore, this figure here may be a little bit misleading. It's actually the in the orthographic version of this, the near clip plane should also be shown here as small as this one. The only thing is far clip plane will also be small, exactly as small as this one. This is like a zoomed in version. I mean, if I could select part of this, I would make it smaller so that they're exactly this size. So if we use the same LRBT parameters in the orthographic projection, the size of this image near clip plane will be exactly the same size as the near clip plane. The difference in perspective projection is that far clip plane is actually much larger, because the rays that as they go beyond this near clip plane, they are getting far away from each other, as we see here. So this in the far clip plane, this LRBT is not observed anymore. Its boundaries are much larger than what we have in this near clip plane. But all the parameters are exactly the same as orthographic projection. We have a near distance, far distance, which are given most usually as positive values, which means that the near clip plane is at z is equal to minus n. The plane here, the image plane, is plane parallel to the xy plane. The plane equation is this: z is equal to minus n. Plane equation gives you the plane equation in which this image window lies on, and left boundary, right boundary, top and bottom boundaries are given as either positive or negative values. They're centered usually at origin 0, 0 in symmetric perspective projection, but it may not necessarily be so. Your gaze may not hit the image plane at the center if L is not exactly equal to minus R. But just in most cases we have this symmetric perspective projection. We have these parameters. Now let's try to figure out the equations, and we are going to use a two-step approach. First, we are going to map the perspective projection into orthographic viewing volume. So what are the distortion? We are going to distort this cutout pyramid. The shape of this cutout pyramid is sometimes called frustum. So if you search for frustum, for example, images, frustum. Frustum is this. So this shape you see here is called a frustum, just cutout pyramid, as you can see. And this frustum is going to be turned into a rectangular prism. First, after we have the rectangular prism, like this LB minus N RT minus F, this is exactly the orthographic. So this step, the second step you see here on the right, this second step is exactly the same thing as we did in orthographic projection. So the problem of perspective projection is to convert this frustum into a rectangular prism. And what kind of a projection we need for that, let's see. What kind of a matrix multiplication we are going to be needing that. So here is, we are going to use the similarity of these two triangles to figure out what the y prime is. And here we are looking at our image window from the side. So here, if this one has a coordinate, actually, this is the side view. So we are not interested in the x-coordinates yet. Okay, we're just trying to figure out the height value. Okay, so this is the side view, which means that we are looking at a particular slice of x here. Okay, so all of them has the same x-coordinates. We are looking from the side. So this is 0, 0. Okay, actually we could have just set this x to 0 to be to make it exactly on the YZ plane. So not to confuse you, okay? So just pick a point on the YZ plane, and let's see how it's going to look like. I'm turning all these x's to 0 just for sake of simplicity here, so that we're looking at something at the YZ plane. This is our I point, and this is the top of the, so look at this 0t minus n, this point, the top of this line passes through, so this is like the upper boundary of your frustum, because this t was your top boundary, t, and b is somewhere here. If it's symmetric, b is going to be somewhere here. Okay, if we have something symmetric, this point here is going to have the coordinates 0b minus n. So this minus n is the distance. So this is your, sorry, I couldn't draw it nicely. So this is your image window, exactly where it's from the side. This is how it's going to span. So this is your image window. Now, in perspective projection, our goal is, given a point like this, 0yz, since we're looking from the side, we're just going to ignore this x coordinate first. Given this y coordinate and its distance, this z coordinate, can we find out what y prime is? Okay, so here, if you look at this, we can use the similarity of these triangles. So whatever this y value is, y prime, so these two triangles are similar. This one has the same angle, and this one, this large triangle, they're similar triangles. So in other words, this distance, y prime divided by y, is equal to this distance divided by this distance. What is this distance? Minus n. What is this distance? Is z coordinate. So we get this equation from similarity of this triangle and the large triangle. And from this, we can take y prime out and write it with respect to the things we already know. So minus n, we know. Y and z, the coordinates of the vertex, we know. So we can actually find y prime. So the same geometric, if we were to look at this from the front this time, or from top, the same geometric configuration, we can derive the same equation for x prime by looking at a point from a certain direction. We get the exact same equation here by again, but we can do that by using similarity of triangles. So this is the other equation we have. So x prime and y prime, which are the projected coordinates on the near plane, could be found by this equation, minus n divided by z times x. So it's actually a scaling of y and x with respect to z. And it's intuitive, right? The farther you are, the smaller the projected coordinates are going to be, because you're projected to a smaller place. For example, if this y was your height, if you have a same height tree, if this was a tree that is somewhere here, if you do the same thing, as you can see, the tree is going to appear much smaller. And because its z coordinate is much larger than the other one, the only thing that changes, this minus n is going to be constant for all of the objects. That this is a constant. So the changing thing for points is that as their z coordinates gets larger, they're going to be projected into a smaller screen space. So these are the equations of perspective projection. But how can we write it as matrix multiplication? And we are ignoring the z dimension for the moment because their z coordinates, the projected z coordinates, are all -1. We are going to write an equation so that we are going to retain their original z coordinates to use them in the depth buffer algorithm part to figure out which object is in front of the other object. Or we are going to just retain them within the cube. Their depth values will be between -1 and 1. Okay, now let's get to the next slide. So how can we, so we have this one, and how can we represent it as a matrix multiplication? I mean, can you write it -n over z minus n over z like this? Can you form a matrix like this? Not a chance, because this z is the z that should appear on the right hand side. This is not your constant. This is not a constant. You cannot have a matrix that is like this, because this z belongs to the vertex on the right hand side. Yeah, it contains the coordinate, z coordinate of the points to be transformed. So it's not possible. We cannot have a matrix like this. Or you need a different matrix for each point. Form this matrix for every vertex separately, but it will make it very inefficient. So our goal is to have like a single instruction, multiple data type of. In order to parallelize these things, we need to have a single matrix that we can apply to many vertices. So we need to have constant values here. And the way to do that is to use homogeneous coordinates. So the homogeneous coordinates, which helped us to write translation as a matrix multiplication in first place. This is how we used homogeneous coordinates in the first place, to write translations as matrix multiplication. Now, again, it comes to our rescue here. Remember that in homogeneous coordinates, a point here in 3D is exactly the same. I mean, these 2 points have the same 3D coordinates, x, kx, ky, kz, k. If the fourth value is k, its 3D coordinates are found by dividing this by that, okay? So if, in other words, if you want to have the new x coordinate to be an x divided by z, we could form this division by z, we could have it as its fourth parameter. This way, we can form these new points by actually with a constant projection matrix. So we are going to, instead of having 1 as the last coordinate from this time on, we are going to, after perspective projection, the last coordinate, the fourth dimension, is no longer going to be 1. It's going to be minus z, so that it's the 3D coordinate. So this is 4D in homogeneous coordinates. In 3D, the x coordinate will be equal to nx divided by minus z, just like we want. All right. And where I went to the end of the slides, and instead of page down, I just hit end by mistake. Let me come back to this. Yeah, so, and the matrix becomes really easy. In order to, now, the z coordinate, as I said, forget about it right now. Just name them A and B. You're just going to have our z coordinate rescaled into 2 values. Actually, this is not very difficult. It's not going to be very difficult to find. What we want to do is something like this. We want to have the new z coordinate, the projected z coordinate, to be between -1 and 1. Okay, we want to retain the original depths. So if an object is, if its z coordinate is at -n, we want zp to be -1. If the z coordinate of an object is at -f, if it's at the far plane, we want its new z coordinate to be 1. Okay, so we want this transformation for the z coordinate, just like we did for orthographic projection that led linear scaling. So in other words, it's like something like this. The same thing we are doing. Something between -1 and 1. It had a z coordinate here. This is a z coordinate. I want this. So this is z coordinate -n. This is z coordinate -f. So if this was its original z coordinate, I want zp to be somewhere here. So the same thing, I mean, z divided by, z minus n. Okay, so the distance between them. Remember, n is always given as positive value. It's not a coordinate. The distance of the image plane. So therefore, then z here, the original z coordinate was something negative. So this will give me the distance to the image plane. And -f minus n. So this divided by this entire should be equal to the new projected zp divided by 2. Again, this distance is 2, okay? So we are going to find ZP from here, again, in terms of Z, I mean, something very similar to the we did here. Why do we have A and B here and these are 0? Because we want to find the new Z coordinate in this form as a linear scaling of, sorry, not X, AZ plus B. So if the third row is like this, the form of the transformation should be a linear scaling, a linear transformation of Z by just depending on Z only. And you can, if you solve this equation, this is what the following slides do, we are going to find what this A and B are. Okay, but if you look at these right now, this n and n, n times x, n times y, and this, the last row now just takes z, multiplies it with -1, and this, after this transformation, the first two rows look like this, and the last row is just going to be -z. And we are going to see what this is. This is going to be our depth value. The depth value will range from -1 to 1, and it's going to be increasing as the objects get far away from the near image plane. And that's it. So I mean, this difficult perspective projection, actually, we will also be able to find it easily by just having the last, making use of the last row now, not 0, 0, 1 anymore, it's 0, 0, -1, 0. So if when you multiply that, this is exactly what I have written here, nx and y minus c, and this is going to have a format like this. And if we have something like this in the homogeneous coordinates, oh, actually I forgot about one thing. If I have this az plus b and minus z here is 3D coordinates, I mean this depth, I need to divide everything by minus z, right? If you divide this minus z, this is the equation you get actually for your z coordinate. It doesn't have a form that looks like this. It's minus a minus b divided by z, because we divide everything by minus z. So I forget about this one. I was trying to find an equation for z, for this a and b, but let's see how we're going to do that. But the other parts, x coordinate and y coordinate, is really easy. Just by similarity of triangles, we just find the projected x and projected y coordinate. Now, for the z-axis, actually, the solution sketch is the same as the derivation, follows the exact same thing that I did. We want this minus n here maps to this, minus f maps to f, and everything in between, actually minus n should map to, I also forgot about the second step already takes care of, okay, sorry, just forget this thing that I did, the linear changing to -1 and between -1 and 1. It's actually done by orthographic projection. Okay, remember this one? This conversion from minus n minus f to -1 is established by orthographic projection. So our goal in this step is not to get z values between -1 and 1 yet. Okay, it's already going to be done by the second step, mapping of this. After the squishing, after we do the squishing, what we need to take extremely care is that this equation, this last part here, minus a minus b divided by z, we need to have it in such a way that if the original z coordinate is minus n, this last entry here should be equal to minus n. Okay, after it's divided by z. So it's something like this. We need to write, let me quickly turn our notation and tell you what we're going to do. So let me tell you again. So if its z coordinate was minus n, after the perspective projection, its z coordinate should remain as minus n. So in other words, what I'm going to do is I need to write minus a minus b divided by minus n. Okay, this was its z coordinate, this should be equal to minus n. So for minus n, this transformation should not change minus n. It should stay at minus n. And this should also be true. Minus a minus b divided by minus f. If its z coordinate was minus f in the first place, it should remain as minus f. Okay, everything here are n and f are given constants. So this gives me two equations with two unknowns. What is a? What is b? We need to figure this out by these two equations, two unknowns, to derive the values for a and b. Okay, so sorry about that. I immediately went to the last step to change the depth between -1 and 1, but that's already done by orthographic projection. So our goal here is to keep the z coordinates as they are. They should not change. The z coordinates should still remain between -n and -f. We don't want them to change. But you may then ask, if you don't want them to change, why don't you just have 0, 0, 1, 0? I mean, why don't we have just a is equal to 1 and b is equal to 0? Your z coordinate is not going to change, right? Or is it? Because if you do that, what will happen? This part is going to be z. I mean, in terms of this one, you're just going to have z here. If you have something that looks like this, nx, ny, z, minus z, you didn't want your z coordinates to change, right? But in 3 dimensions, what will happen is this: if you multiply all the values with this minus z, if you multiply it with minus z, which means that you actually turned all of your z values to -1. You didn't retain the z coordinates. Z divided by minus z. Z divided by minus z, their z coordinates became like this. So everything is divided by minus z. Our goal is to figure out a transformation such that even after we divide whatever value we have here by minus z, it will still remain as z. So therefore we form these two equations, minus a minus b divided by z. If your z coordinate is -n, it should still give you the same z coordinate. If your z coordinate is -f, it should still give the -f. These are the two boundaries of your image window, so that by satisfying these two equations, you can find what a and b is. So that's what is done. Actually, this is what it means. -n maps to -n means that if you originally had the z coordinate of -n, it should, after the transformation, after the division by your minus z coordinate, it should still be -n. So here, yeah, it's right here, -n plus b over n. So this was minus b. So the same equation here. We should get this one. This is one equation. This is the other -f equation. We can rewrite them like a is equal to f plus n here, b is equal to f times n. So two equations, two unknowns. If you solve for them, actually we have just solved for them. a becomes f plus n, b becomes f times n. So all you need to do is write f plus n for your a value, f times n here. You may try this out, for example. What will happen if your coordinate is -n? What will happen is that you're going to multiply it with this and divide it by f times n. Add f times n to that and divide it with your -n z coordinate, and you will end up with -n at the end. So this matrix is squishing that frustum, which is that cutout pyramid, into a rectangular box. Okay, and this is established by having a 4-dimensional homogeneous coordinates. In that homogeneous coordinate system, it is after the division, after the perspective divide, this dividing by the 4th dimension is called perspective divide. After that, we have in 3 dimensions, we have a 3-dimensional coordinate system. We have ourselves a nice, distorted, perspectively distorted coordinates. So this is step 1, which converts this. Let me come back to here quickly. Yeah, this one. So that matrix that you see here, which was multiplying everything by n, and with the fourth row different than 0, 0, 1, the fourth row was 0, 0, minus 1, 0, it converts the coordinates to this rectangular box like this. Now we are in this space, and after that, when we perform the orthographic projection that we have figured out, everything is now and becomes in canonical. So if you multiply these two things together on the left, so this is performed first, then this is performed after that works, because we are right multiplying. Our vertex appears here, which means that this is the first projection that is applied, this is the last projection that is applied. These two together, we call it perspective projection matrix, and if you multiply them together, it appears like this, that 2 divided by r minus l, there is now a factor of n here. The last row remains the same, 0, 0, minus 1, 0, and again, you don't need to memorize these matrices, but if you're going to want to perform perspective transformation yourself, so this slide has the solution directly to, if you're going to code it, for example, this slide gives you the perspective matrix. All these parameters here, R, L, T, B, F, and N, they're just constants. They just define that frustum. Multiplying these points with your world coordinate or camera coordinate system points will give you all the points that are between -1, 1 will be the points that will be visible on your image plane. The perspective divide that I mentioned is performed afterwards. After the perspective projection, the W coordinates of the transformed points will not be 1. For the perspective projection to take effect, each point is divided by its W coordinate to get back to 3 dimensions. This process is done again on the GPU automatically in the forward rendering pipeline in parallel. So every point is divided by its W coordinate, and our 3-dimensional coordinates that appear now on the image. This will be its projected X coordinate on the image window. This will be its projected Y coordinate on the image window. And this will be its depth, which changes between -1 and 1 right now. We are going to actually change this back to 0, 1, not -1 and 1. It's going to rescale to 0 to 1. It will, because when you get the depth buffer values, you're going to see that the objects that are closest, that are on the image plane, they have depth values 0. And the objects that are very far away, that are at the far plane, they will have depth values to be 1. So it's a standardized depth value between 0 and 1 is what we are going to have later. But right now, after this step, these values are between -1 and 1. Okay, don't forget about this. Everything, all the coordinates that, for the points, for the vertices that we see, they are between -1 and 1. It's not, there may be points that are outside the weaving volume, which will have different values, larger or smaller values than -1. And after perspective, so this concludes projection transformation. The last thing that is done is something done very simple actually, which is called viewport transformation. Now the standardized coordinates, which were between -1 and 1, are converted to pixel coordinates, which the lower left of your image window will have the pixel coordinates 0, 0, and the upper right corner of your viewport will have the coordinates nx -1 and y -1. So the viewport transformation maps all the projected points here on this canonical view volume now back to a non-standardized image window, which has resolution between 0 and nx and y. So these are called the screen coordinates, or sometimes called window coordinates, is established by this viewport transformation. So it's just a linear scale, therefore it's very simple. It's not a very difficult thing to do. All the ranges that are between -1 and 1, they are transformed to between -0.4, -0.5, because this corner of the image window, the center of this pixel is 0, 0. Therefore, this corner, its coordinate, the coordinate of this corner is minus 0.5, minus 0.5. And our units are in such a way that a pixel width is 1 unit. A pixel height is 1 unit in the y-axis. Okay, so our units are now 1, 1, 1. 1 pixel has a width of 1 unit after this transformation. So we're scaling everything with this nx divided by 2. Why divided by 2? Because the original distance was not 1, it was 2. From minus 1 to 1, it was 2. And now we're scaling it to nx. The scale factor becomes nx divided by 2. And yeah, this, and also, as I said, this happened, the scaling of the depth values, which was minus 1 and 1, transformed back to 0, 1 for later use in depth testing, occurs here at viewport transformation. I mean, you may ask lots of questions. I mean, there's lots of things to question here. Like, why did we have z values between minus 1 and 1 in the first place? Why didn't we try to directly convert them to 0, 1? Why in the canonical view volume it's like this? It's just a choice of implementation, or these are just some conventions. We could have done this conversion to 0, 1. I mean, if you look at this, it's doing nothing. If you look at the z coordinates, it's doing nothing but just transforming these values between minus 1 and 1 to 0 and 1. This could have been done in the previous step. But again, if we were to perform clipping and culling at the canonical view volume, maybe having all the ranges standardized to minus 1 and 1 may help us in certain equations, maybe. Okay, but this viewport transformation, as I said, is nothing but scaling all the standardized 0, 1 coordinates back to 0, 0 to nx, ny, and the depth values to between 0 and 1. Now at this point, something really interesting happens here. Our matrix is not 4 by 4. It's actually 4 by 3, right? I mean, the third dimension, we don't need it anymore. I mean, the fourth dimension, W component, we don't need it anymore. At this point, we will not do any translation. The only translation occurs here. But I mean, we are multiplying it, as you can see. The W component is not needed. We can multiply this with a 3 by 1. Actually, 4 by 1 matrix in which the fourth dimension is just 1 to do this scaling effect. Okay, so actually this concludes all of we were able to finish all the transformations, camera transformation, projection transformation, and the final thing, viewport transformation. The final slides are about something we called about the depth buffer algorithm. So I just want to mention them in the last 5 minutes. So we will finish all of the slides that are, so the midterm includes topics all the way until this set of slides, including slide 35, but we're almost done. And on Thursday, I'm going to, we will have a class. I'm going to do a quick review of everything, and I will answer questions if you have any. There's a question by side. Let me read it to you. So in the canonical view volume, the xy minus 1 plane, yeah, actually that xy, the z is equal to minus 1 plane is correspond to nearest object to the camera. Exactly. They are, the camera is the objects that are closer to us, we will not be able to see them. Although the focal point in perspective projection, for example, if the focal point is, so it's going to be something like this. If this is your eye point, the focal point, if this is where the near plane is, in the canonical view volume, this is at z is equal to minus 1. So the closest objects that we can see will be exactly at z is equal to minus 1. If there's an object that is here, we will not be able to see them. Okay, so objects that are here, we don't see them. Okay, so actually they will be converted to Yeah, this will be -1, this is going to be 1. Yeah, so the closest objects are z is equal to -1, far away objects are z is equal to 1. As you can see, this is like inverted. The z coordinates is now inverted in the canonical view volume. Yeah, the nearest objects are at z is equal to -1. That's a correct observation. Now, one thing that happens is that if you look at this figure, which shows so this is the z value, this is the z prime value. So this is where the near plane is at f and the far plane is at 200. So if we have this near plane and far plane at these values, 10 and 200, if you look at, if this is your original z value, which now changes, its z coordinate is between, as you can see, after the perspective projection and after the viewport transformation, your depth values are changing between 0 and 1, right? Your z value, the nearest, if you are at z is equal to -10, your depth becomes 0. If you were at z is equal to -200, your depth is going to become 1. But look at, we would expect, if mathematically we wouldn't expect that, but it's not linear. I mean, as your z coordinate gets larger like this, your z prime is not a linear transformation of your z coordinates. Your z here, well, what did I do? I just undid my clear drawing. So your z coordinate, your depth values that we have found by dividing by this z, is actually non-linearly transformed. Okay, so in other words, objects that are which are very close here, between -10 and -20, objects that occupy this in this space, their depth values occupy almost half of your depth space. Look at this. Objects which are 10 units apart in your world, in your scene, their depth values range from 0 to 0.5 here in this depth space. Objects that are between -20 and -200, objects that are between -20 and -200, that occupy a unit of 180 units, they occupy the rest of the z is with them. So we are able to distinguish objects z values that are very close to us. But when the objects get far away from us, what you see here is that the distinction between their z values, their depth, so the differences between their z values is not going to be that much, although their distances are like they may be 5 units away here, but their z values will be very small. So this will result in, because of our precision, floating point precision, objects that are far away, which you think that one object is behind the other object, because of our floating point precision, we will not be able to distinguish objects that are, for example, 1 unit behind the other object. They will appear as if they're at the same z value. Their depth values will be very close to each other, and because of these floating point or double imprecision, what we are going to have is something called z fighting. Objects that are in the far, if they're far away, although the red rectangle is behind the green rectangle, this being behind will not be able to, our depth of our algorithm will have difficulties in figuring out at certain pixels who is front, who is at the back. So one thing that you can do to solve this is not have this far plane as very far. If you have this, for example, 20,000, the result will be more pronounced. The z fighting will be worse. So trying to have this far plane as close as, for example, 200 is a really good value. It's not that bad. But if just to see everything clearly, do not make your far plane at 20,000, okay? Because I want to see everything. Let's have the far plane at 20,000. But when you do that, don't forget that things that are seen to you, their z values, you will see this z fighting effect a lot. So try to limit the difference between near and far planes practically when you're designing games or stuff. Okay, so this is exactly repeating what we told. So to avoid that, we want to have this depth range between near and far planes should be kept as small as possible for keeping this compression less severe. And finally, in summary, the point in X, the point that is given to us in the world coordinate system, it can be transformed to the viewport coordinates, to its viewport coordinates by multiplying. If we had, let me write something else here. Let me also copy this one. Here I'm going to call it modeling transformations. Okay, so if these are the coordinates you read from a file, when you're designing your world, you move that point, you rotate that point, maybe you first perform modeling transformation. Oh, it's in the next slide. Thanks. And we have the camera transformation to move everything to the camera space, then perspective transformation. At this point, we do perspective divide, then viewport transformation. Now, at this point, XVP, YVP, and its depth value. Now we can jump onto our rasterization stage where we actually fill in the pixel values. Yeah, here is the modeling coordinate system we have here. So this is actually what you will be implementing in your second assignment after the midterm. We will have the second assignment in which you're going to have your own software rasterizer implemented. So we will give you again the same models provided in XML files like this, and we will give some scene description, move objects to different places. You are going to implement this stage will be your first, this will be your vertex processing stage, in which all the vertices now are going to be mapped onto pixels, pixel coordinates, and their depths will be found. Then after you have the pixels, the problem, I'll just spend one more minute here. Oops, I couldn't click on annotate. Yeah. So after that, we now have a different problem. Forget about the world and everything. Just we have an image. We have a triangle on the image. We want to draw this triangle on the image. How do we do that? We know it's this pixel, this pixel, this pixel. Now, which pixels should be illuminated? So which pixels, in order to draw this triangle, how do you do this triangle drawing on a 2D image pixel space? Which pixels should be turned on, turned off? This is what we call rasterization, and we are going to do it. We are going to see line drawing algorithms after the midterm, how we can interpolate certain parameters. The color should be interpolated nicely along the triangle. We are going to see about those things before your second assignment. You'll also be able to implement those in the second assignment, but that's it basically. Okay. Yeah, we must reconstruct the triangles after that. We must decide which pixels belong to which primitive, which fragment of, yeah, all these things we'll decide next on the forward rendering pipeline. Okay, so that's it from me for today. We have finished everything that is included in the midterm exam. On Thursday, I'm going to do a midterm review and answer your questions if you have any. Okay. Thank you very much. See you all on Thursday. Bye-bye. I will stop recording now.